latter half of the year 1966 marked the 5th anniversary of several key events in the manned spaceflight program. In 1961, at NASA's Langley Research Center, Hampton, Virginia, the Space Task Group, charged with the responsibility of developing manned spacecraft, was renamed the Manned Spacecraft Center, with Dr. Robert R. Gilruth as director. A permanent site for the new center was selected near Houston, Texas. This is a 1961 view of the 1,620-acre site on the edge of Clear Lake. By the end of 1963, occupancy of the Clear Lake site was underway, and by the end of 1966, all 33 originally planned main buildings were being utilized as a permanent working home for 4,800 NASA manned spacecraft specialists. Comparing spaceflight missions 5 years before, in 1961, America's heaviest orbiting payload weighed 3,000 pounds. By the end of 1966, NASA was preparing for the first flight of the Saturn V launch vehicle, capable of orbiting a payload of 250,000 pounds. In 1961, astronauts Shepard and Grissom made their suborbital flights, but the nation had not yet placed a man in orbit. By the end of 1966, 4 astronauts had completed orbital flights in the Mercury program, and the complete Gemini program had been successfully accomplished, including 10 two-man orbital missions. It was on December 6, 1961, that Dr. Gilruth announced the Gemini program. The initial objectives were threefold: to rendezvous and dock 2 spacecraft in Earth orbit, to achieve long-duration space flights to accumulate medical data, and to accomplish controlled land landings. Although land landings of manned spacecraft were not attempted, controlled re-entry and other actual accomplishments of the Gemini program far exceeded the initial goals. The 3 final Gemini missions were flown during the latter half of 1966. They exemplified the achievements of the total program. On July 18, the Agena rendezvous vehicle for Gemini 10 was launched at 2:39 p.m. Central Standard Time. Less than 2 hours later, at 4:20 p.m., after a faultless countdown, the Gemini 10 spacecraft was launched. Four hours, 26 minutes after liftoff, astronauts Young and Collins had made visual contact with the Agena. 84 minutes later, the 2 vehicles were docked. Using the primary propulsion system of the Agena, the combined vehicles were then boosted to an altitude of 475 statute miles, a new manned altitude record, and the first time in spaceflight history that a manned spacecraft had acquired and used the propulsive power of another vehicle already orbiting in space. But there was more to come. The Agena from Gemini 8 was still orbiting in space. After its first mission, its main engine had been fired by ground command to boost it to the higher altitude. The next day, Gemini 10 also rendezvoused with that Agena. Another space first was achieved when astronaut Collins left his spacecraft to retrieve a micrometeoroid experiments package from the Agena. This he was able to do despite the fact that an attack of eye irritation had cut short his stand-up EVA the day before. At splashdown about 3:06 p.m. July 21, the Gemini 10 mission had made history as the first mission to achieve in one flight all of the enlarged goals of the Gemini program: rendezvous, docking, combined vehicle maneuvering, extravehicular activity, and controlled re-entry. But more space firsts remained for Gemini 11, which was launched on the morning of September 12. Using onboard computation procedures, astronauts Conrad and Gordon achieved rendezvous with the Agena vehicle about 3/4 of the way through the first revolution. Docking was completed about 1 hour and 34 minutes after liftoff, before beginning the second revolution. 2 periods of extravehicular activity were scheduled to be performed by astronaut Gordon. The first umbilical EVA was curtailed due to spacesuit heat and unexpected exertion, which caused the astronaut to perspire excessively. This partially blinded him, but he was able to attach a tether linking the Agena and Gemini vehicles. Using the primary propulsion system of Agena, the docked vehicles once again set a new altitude record, an apogee altitude of 850 statute miles. Several photography experiments were carried out. After another Agena firing had returned the two vehicles to a lower orbit, they were undocked and separated, except for the tether, which was then used to perform a station-keeping and artificial gravity experiment. Linked together by the 100-foot tether and retaining a slight tension, a spinning motion was imparted to create a small gravity field, constituting the first such exercise in tether dynamics. The exercise confirmed the feasibility of station-keeping in the tethered mode to save fuel. A planned gravity gradient stabilization experiment could not be done because of spacecraft control system problems. Re-entry of Gemini 11 was fully automatic. Splashdown occurred 71 hours and 16 minutes after liftoff, just 2 miles from the planned impact point. Due to the extravehicular difficulties encountered in Gemini missions, the ability of men to perform work in space became one of the major questions raised by manned spaceflight experience. It was decided to test this capability more thoroughly on the final Gemini mission, Gemini 12. For this reason, astronaut Aldrin spent many hours underwater training for extravehicular performance in the simulated zero-gravity environment produced by the buoyancy of water in a pool. His training and practice included egress from the spacecraft, installing the telescoping handrail, performing various work tasks, assuming positions of rest, and familiarizing himself with such aids as the handholds in the area of the Agena docking collar. The Gemini 12 spacecraft was launched at 2:46 p.m. on November 11, an hour and 39 minutes after the launch of its Agena rendezvous vehicle. Rendezvous occurred on the third revolution, and astronauts Lovell and Aldrin completed the first docking at 4:16 p.m. The Agena's secondary propulsion system boosted the combined vehicles to an orbit of 139 by 154 nautical miles to position the craft for observation and photography of a total eclipse of the sun over South America. On the second day of the mission, astronaut Aldrin performed the first of 2 stand-up EVAs for photography and scientific experiments. November 13, the next day, astronaut Aldrin, aided by a 30-foot umbilical strap, left Gemini 12 and performed measured work tasks at the Agena docking adapter and at the spacecraft adapter section. His hours of specific training and new devices to help him retain stability while working in space paid off in a highly successful 2-hour and 9-minute extravehicular performance. This included working with tools and accomplishing several mechanical chores for the first time in space. After separation of the two vehicles, except for the tether, Gemini 12 also accomplished tethered station keeping and the space program's first gravity gradient maneuver with Agena. The gravity gradient relationship was established within the time required for the vehicles to complete 1 revolution of the Earth. They remained tethered for 4 hours and 17 minutes. In a second stand-up EVA, astronaut Aldrin was again very successful in his experiments and photography. Splashdown on November 15, 3 miles from the carrier Wasp. Recovery operations and post-flight debriefings and evaluations brought to an end the highly successful Gemini program. Throughout the Manned Spacecraft Center for many months, the bulk of activity had centered around the Apollo spacecraft and crews. The changeover from Gemini to Apollo during the report period is exemplified by the Flight Crew Support Division's Dynamic Crew Procedure Simulator. Its value was well proved in simulations of Gemini missions, which gave astronauts training in events and contingencies such as launch aborts, where kinesthetic, that is, muscular sense clues must be relied upon. The simulator was designed as an all-purpose trainer. Here, it is in the configuration required for dynamic simulations in the command module phases of an Apollo mission. The new training was made possible simply by changing the crew station. In this configuration, An Apollo Command and Service Module station has replaced that of Gemini, as astronaut Stafford gains experience with conditions he might encounter in actual flight. By again replacing the crew station, Apollo lunar module conditions can also be simulated. Another important simulator of the Flight Crew Support Division has been the Apollo Mission Simulator, in which astronauts can go through a complete lunar mission in a simulated command and service module. In the report period, in an area adjacent to the Apollo Mission Simulator, there was installed a lunar module mission simulator for those phases of an Apollo mission performed in the lunar module. The lunar module mission simulator also relies basically on television visuals, with the circular area on the ceiling representing a lunar map. This gives the effect of having the lunar surface below the spacecraft, as exercises are simulated involving both approach to the command module and leaving the command module after separation. Another type of lunar module simulator is this Lunar Landing Research Vehicle. It is a wingless, free-flying platform made of lightweight tubular trusses with a total weight of less than 4,000 pounds. In it, and its successor, a lunar module training vehicle, astronauts can simulate the last 2 minutes of lunar landing, the most difficult phase of lunar module flight. 2 of the research vehicles were delivered in December to MSC's Ellington Air Force Base facility. Earlier, model number 1 was successfully flown nearly 200 times at NASA's Flight Research Center at Edwards Air Force Base by NASA test pilots and MSC pilots. The vehicle has a vertically mounted, double-gimbaled fan jet engine yielding 4,200 pounds of thrust, plus 16 attitude control rockets for roll, pitch, and yaw control mounted at each corner in clusters of 4. Controlled throttling of the main engine removes 5/6 of the Earth's gravitational pull. The vehicle can hover and be set down at speeds of 2 to 6 feet per second. On July 26 began the first major test of a manned Apollo spacecraft in Chamber A, the larger of the 2 thermal vacuum chambers at the Space Environment Simulation Laboratory. The first 3 days of the test were unmanned to measure temperature stresses and heat shield alignment. The manned test followed beginning August 1st and lasting 8 days, with 3 Flight Crew Support Division engineers in the command module. The test consisted of a cold soak, including evaluation of the environmental control and electrical power subsystems, and determination of the thermal response of the service module bays, containing such major components as fuel tanks, fuel cells, and reaction control systems. Fuel cell loss tests and cabin depressurization were also conducted in a thermal vacuum environment like that at 87 miles above the Earth. The crew's ability to work efficiently and relax in comparative comfort for the 8-day duration of a lunar mission was confirmed. On September 30, 50 miles off Galveston Island in the Gulf of Mexico, Spacecraft 007 was lowered from the retriever and flipped to an apex down position. 2 electric air compressors inflated the 3 uprighting bags, and within 6 minutes the command module had been uprighted to a stable apex up position. With waves at times reaching 12 feet, this was the first manned sea test of the Apollo command module seaworthiness and of post-landing subsystems. The crew consisted of engineers from the Flight Crew Support Division and the Landing and Recovery Division, who emerged 2 days later after a highly successful test. Proximity to the ocean and year-round climate for training and tests were 2 of the reasons for the selection of the Clear Lake site 5 years before. But not all MSC work is performed near Houston. Astronauts and MSC engineers continued during the report period to spend a great deal of time at the plants of contractors. Over the years of gaining experience in manned spacecraft technology, test procedures have been streamlined, with the result that spacecraft operational checkout times are continually being reduced. Manned Spacecraft Center personnel also direct and staff operations at NASA's White Sands Test Facility in New Mexico, where propulsion and power systems are subjected to a variety of tests. Here, engineers of the Landing and Recovery Division are observing the second test drop from a 5,000-foot altitude of a Gemini boilerplate on a Mercury parachute in a test of improved electrically operated parachute reefing cutters. feasibility of the new cutters was demonstrated. On August 8 at White Sands, MSC engineers began a 14-day static firing to simulate Apollo mission demands on the surface propulsion system. 8 firings of the 21,900-pound thrust engine, totaling about 120 seconds, were separated by coast periods lasting as long as those planned for the first manned flight. Throughout the 14 days, the liquid propulsion system was kept pressurized at mission levels. During the report period, other mainstream results from engineering and development work begun months and years before continued to emerge. For example, the first astronaut familiarization runs were conducted on board MSC's 50-foot arm rotary accelerator. And day by day, other vital, patient engineering and development work continued to prove out manned spacecraft subsystems, components, and materials. Experiments continued with a newly installed system developed to obtain data on ablative heat shield material during simulated re-entry. The system utilizes closed-circuit television and X-ray equipment for monitoring and measuring. A 35-millimeter camera records the results. Sample material is heated by an arc jet to re-entry temperatures. Such data as the depths of charring are used in defining the operational limitations of the Apollo spacecraft's thermal protection system. Another typical investigation in engineering and development was that of a new net couch for long-duration missions. The couch and an instrumented dummy were subjected to 50G impact simulations, reduced at 3 locations within the dummy to 20 to 25G stresses. Drop tests were also conducted to demonstrate and verify the force attenuation characteristics of the net body supports. Such a stowable net couch is being designed for possible use in Apollo applications missions. At MSC's Mission Control Center in December, the Mission Planning and Analysis Division demonstrated a prototype lunar mission display, similar to that which will display the position of the spacecraft during lunar missions. In this scene, the moving spacecraft is represented along the upper line. Its position projected down to Earth is revealed by the figure moving along the lower line. The actual display, of course, will move at real-time rates. The second half of 1966 was not without its problems. On October 25, during a pressure test at North American Aviation, a service module fuel tank ruptured. The test was conducted with alcohol and freon simulating the hypergolic propellants. The failure was traced to the stress corrosion effect of methyl alcohol on the titanium tank. Problems were also encountered in the Apollo environmental control system. Late in October, the porous nickel filter plates of a water boiler type of heat exchanger caused clogging, which reduced flow and cooling efficiency. Cooling is effected by circulating a water glycol solution through the spacecraft and evaporating the heat by means of radiators, supplemented in peak periods with the heat exchanger. To correct the clogging condition, the nickel plates were replaced with stainless steel filter plates. In October, a second manned test of ground test, Spacecraft 008, was conducted in Chamber A, with astronauts Givens and Kerwin and technologist Gagliano, beginning October 26 and lasting for 6 days. Environmental control system performance was tested with spacecraft subsystems in modes representative of those planned for the first manned Apollo flight. With 550 NASA and contractor employees involved in round-the-clock support of the test, all objectives were met. Late in October, the decision was made to go ahead with the first manned Apollo flight. It would be an open-ended Earth orbital mission lasting up to 14 days. Here, the prime crew assigned to the mission, astronauts Grissom, White, and Chaffee, practice egress from an Apollo boilerplate model onto the 3-man life raft of the Block 1 spacecraft Earth orbital missions. Recovery training was complete through helicopter sling pickups of the astronauts. The value of astronaut Aldrin's underwater training in a pool in Maryland led to the construction of a large neutral buoyancy tank at the Manned Spacecraft Center. The new MSC tank was filled in December. In it, astronauts will train not only for extravehicular activity, but for movements inside the comparatively roomy Apollo spacecraft. The neutral buoyancy tank was also used for the first tests in a simulated weightless environment of a model of the airlock being developed for long-duration Earth orbital missions of the Apollo Applications Program. The 5-ton, 65-foot diameter and 15.5-foot long airlock and a docking adapter will be positioned next to the S-4B stage hydrogen fuel tank. After the fuel tank has been emptied and the vehicles are in orbital flight, the command and service modules will dock with the airlock. The crew will then enter the airlock, pressurize the empty tank, and equip it with fuel cells and other necessities stowed in the airlock. The S-4B tank can then serve as an orbiting space laboratory or workshop. New facilities such as the neutral buoyancy tank and the lunar receiving laboratory, on which construction was begun during the report period, confirmed the foresight of the men who selected the site for the Manned Spacecraft Center 5 years ago. Ample elbow room exists for adding new facilities as demanded by the ever-developing manned space program. The lunar receiving laboratory, which will be complete by the end of 1967, will provide 84,000 square feet of floor space. A central complex where samples of lunar surface material collected by Apollo crews will be received, quarantined, examined, and later processed for distribution to scientists throughout the world for study and analysis. It will also be equipped to quarantine spacecraft and crews after their return from the moon. Another advanced development will reduce radiation hazards for astronauts on Apollo lunar missions. This is the Solar Particle Alert Network. A globe-encircling chain of solar telescopes, such as this one in Australia, will be part of the network. By extreme close-ups of sections of the sun, they will gather data on solar flares and other phenomena related to discharge of radiation. Such data will help mission planners determine the safest dates for manned missions in outer space. The October go-ahead for the first manned flight was influenced strongly by the success of the 2 unmanned Apollo missions, which were completed earlier in the report period. The first of these was launched on July 5 and was the second successful Apollo uprated Saturn I mission. Its purpose was to verify the design and operation of the hydrogen-fueled second stage of Saturn I, the S-4B stage, for its use as the third stage on Saturn V. As the third stage of Saturn V, the engine will have to be capable of shutdown and restart to boost the spacecraft out of Earth orbit into a translunar flight. The mission did not carry a spacecraft. Instead, the S-4B stage, the instrument unit, and a nose cone were launched into orbit as one 92-foot-long, 59,000-pound satellite, the heaviest yet placed in orbit by the United States. For 3 revolutions, onboard television cameras transmitted pictures as the liquid hydrogen sloshed around during boost, then calmed, then settled to the bottom of the tank. During weightless orbital flight, the hydrogen behaved satisfactorily in both vented and unvented tank conditions. The mission confirmed the ability of the S-4B to restart in the weightless condition. Other experiments were also successful. On August 26, the third Apollo uprated Saturn I mission was launched in a 94-minute, 18,000 statute-mile suborbital flight to verify systems for manned Earth orbital missions and to conduct a definitive atmosphere entry test of the spacecraft heat shield. After separation from the Saturn launch vehicle, a 215-second burn by the surface propulsion system boosted the spacecraft to a peak altitude of 660 nautical miles. A second burn of 85 seconds by the main engine placed the spacecraft into a high-heat atmosphere entry position. 2 more firings of the surface propulsion system of 3 seconds each were made primarily to test the engine's restart capability when propellant supply is low. This was the first flight for the fuel cell system, the unified S-band system, and the Apollo guidance and navigation system, which controlled the engine firings and modulated the lift vector for controlled entry. The long-duration entry, reaching a velocity of almost 19,000 miles per hour, subjected the heat shield to heat loads of approximately 20,000 BTUs per square foot. The maximum surface temperature was about 2,700 degrees Fahrenheit. Recovery and analysis of the heat shield ended this 13th successful unmanned Saturn mission. The historical series had begun 5 years before, in the fall of 1961, with the original suborbital Saturn I flight. As the year 1966 drew to a close, in the MSC Auditorium, a formal award ceremony honored government and contractor personnel for exceptional, distinguished, and outstanding services. The ceremony underscored the progress in manned spaceflight made in the 5 years since the founding of the Manned Spacecraft Center. Progress which is exemplified in particular by the successful completion of the Gemini program. Its original goal of rendezvous and docking had been achieved several times. Its original goal of obtaining medical data from extended missions had been attained, and it proved man's ability to adapt to conditions such as weightlessness in long-duration missions of 8 and of 14 days. Surpassing Gemini's original goals, valuable experience was gained in extravehicular activity. In experiments ranging from the effects of the space environment on frogs' eggs to a variety of photographic experiments. In tethered station keeping. In the use by spacecraft of the propulsion systems of other vehicles for both orbital and plane changes. Also, both manual and controlled re-entry experience was acquired. And the value of having men on board spacecraft to increase reliability and the developing potentials of space missions was confirmed. Taken as a whole, the Manned Spacecraft Center's development, testing, and operation of Gemini spacecraft and systems constituted another fundamental technological triumph in the progress of man in space.